right, so everything looks good. Guys, we are going to talk about queue data structure or queues data structure. This is his data structure which works on FIFO principle, which means first in, first out. Okay, it basically means that the first element that is added to the list is going to like execute or rather the first element that is added to the data structure is going to be deleted first. Okay, we are talking about like inputting some numbers in the queue, and then we want to remove some elements from the queue, right? So we are adding from the end and removing from the beginning. That is what we are doing here. In this data structure, the element we can also say that queue is a last in last out. It works on last in last out principle, which means that the element will be added from the uh, well, it's last in last out because the element that enters in the queue lastly, right? So that element will be removed in the end when all other elements are removed. So it's kind of like that. So the basic idea is to enqueue from the end and dequeue from the beginning, which means that if we write a program and use linked list data structure, and in that program we give the functionality of user the functionality to users in order to let them add elements at the end of the linked list and remove element from top of the linked list, then that is going to be called a queue. So that's what I think, that is exactly what I am trying to do here. As you guys can see, each node contains the base address of its next node and last node is containing null in it. So you can see the base address of this node right here, the one that cursor is pointing to, this node, its base address is 100. The one after that is in the like queue is the node with its base address 900. So you can see that the previous element has the base address of the element which was added after it, right? So that we can access this element if we have the head pointer set to this first node. So you can say head contains the you can see the head contains the base address of the first node. That's what I'm saying. The head is containing 100, which is the base address of the first node. Tail is containing 9000, which is the base address of the last node. We can use tail to in-queue elements since we have to in-queue from the end, and we can use head to dequeue elements as we have to dequeue from the beginning of the list. So I hope you guys get the concept. Now let's work on it, and if there is an error, like sorry about that, if there is an error in the way we are implementing it, then we are going to stop at that point and re-watch this picture, or think about some different way of implementing it so that everything works out perfectly. Now I'm going to open this code blocks application in order to write this code. I have written nothing in here, so that what I think I made a mistake, or it might have been a better, or it would have, or it, it it might be a good idea to write the code first, but I think it's not that bad to write it on camera either. So let's go. I'm going to declare two functions here. uh, first of all, I'm going to write these two functions because these are very important functions. Function prototypes, because let's just declare the function prototype first, and then we are going to write it. Okay, so first of all, what should we do? I think we are not going to take anything as input, so let's just do void in queue, right? Void in queue, and that's pretty much it. It's taking nothing as argument. Again, void dq. This function is taking nothing to. The function of this in queue is to add. It's not that. It's add elements. Oh shit. Add elements uh, to the queue, or you can say a linked list too, because we are using linked list data structure to implement this. uh, Alright, so this is to remove elements uh, from the queue. If there is nothing in the queue, then if there's like literally nothing in the queue, then a dq should return that the queue is empty, there is nothing in there, right? And the underflow condition, that there's nothing in there and we are still trying to dq, which is which should give an error, right? And that's pretty much it. But one thing that I forgot to do first is really important too, is to declare the struct data type. Struct, let's say q. What are we going to do here? Now we have to write what do we want to enter. I don't know. We can use characters, right? We can do characters. I don't want to take risks here actually, but yeah, let's just take int. Later on we will update the code and then redo it. So let's say int data. I don't want to take risks here. Now int data, and then we want the pointer to the next node. So remember, it's next in here, it's not previous, it's next. In stacks it was previous because we were moving heads on top every time and it was containing the address of the previous node. But here it is not the condition. Here we are going to contain the base address of the next node, because in queuing is the operation that happens uh, from the end of the queue. It doesn't happen on like on top, or from on top of the queue. So yeah, struct struct queue and this pointer to the next element in the queue. And then what do we want more? We should declare uh, global variables head and tail actually. Head, yeah. So let's go struct queue, and its pointer to newly created node, because nodes are created all the time, and this variable will this pointer variable will help us create these nodes. Initially it will be null. Struct queue head, right? and head will contain null too. It helps us traverse through the list. And let's do tail. We might change stuff because I'm not perfect and this is the first time I'm writing this code. If we were to be able to write programs just like this, then things would get really easy, but that's not the case. A lot of errors happen all the time. So these are global variables. Have I done any mistake? Last time I did some mistakes. Let's see if there is. Listen, these are not used to, so there should be some errors. uh, it's F2 guys, so when you click F2, error conflicting types for head, it is the same thing that happened last time around. Alright, so we are going to do this and this. Okay, they basically tell you to typecast. It's this, right? Alright, let's see. Yeah, it doesn't give that kind of errors because if you don't do this kind of like a declaration, then there will be this error. This you saw it, right? Normally if I would have declared these variables inside well, yeah, if we would have declared these variables within this main function, the main method, then that error would not have shown, but it happens. They tell you to basically typecast. I don't have to put anything here, and there is no like requirement to typecast or anything like that. Let's just it's better to like declare things in just one line, right? And these are the operations enqueue and dequeue. We can say void display because every time we need to display something to, right? So this is another one of the features that we will give. We will also give this feature of peaking at the top of the list, a queue, or rather peaking at the element which was added to the cube, queue. What is it? Peak operation. Alright, so none of these take any like to look at the last element added to the queue. Alright, and then display function. It's simple to display the elements of the queue, or rather in the queue. So these are the four features that we are going to add. Alright, what's this? This is nothing that we need to worry about. By the way, I wanted to do it earlier, but this right here I would like to explain it to you if you have not studied like structure uh, keyword or struct keyword. Struct is just a keyword, right? Q q is a tag name. You can write pretty much anything here, right? You can write my name, you can write your name, but q is self-explanatory. It explains that what we are trying to create with this, by allocating this much, the amount of memory required, uh, is we are using it to create nodes and link each other to create queues. So that's why I have written the tag name queue. This one is going to contain some integer data. This will contain the address of the next node, and the last node will contain last node's next field will contain null in it because it's not pointing to anything. If we enqueue anything in the list, then it's going to be stored in the next part of the previous one. Now let's do some printf stuff. We are going to let them know what their options are. Dequeue from the queue. Sorry about not speaking for so long. Let's keep writing these. What we are doing here is we are telling or letting users know, uh, we are just letting users know what they have to do, what are the options that they have. And now the last one. Oh, we have to give them another functionality. Listen, this should be another one actually. Exit function, we will give them this option of exiting. Alright, so these are the four options. Let's just cut these. And in here, what should we do? These options, and then from there users choose, and then switch statement runs. Yeah, so that's what we are going to do. Damn, this happens all the time, and I shit. All right, let's just copy this much space. Right, copy this much space, and then paste it here, and things are properly indented. Indenting is a problem. It's a big problem, and I hate it. I literally hate it. I despise this fact. All right, so here int cont t new is, nah, we are not going to use continue. Continue is just one of those, like, what should I call it, damn it, it's keyword, so we are not going to use that. Let's say yes no. Yeah, last time I used yes no, so let's use yes no. And yes no is equal to 1. If user enters 0, that means they don't want to do operations anymore. Since this is the big do one, so let's go do while, and it's yes no. Users, uh, now o will be smaller. This this second elements for second, this listen, yes no are two different words, so the second words, uh, first letter will be capital, and that's one good way to denote stuff, to know to do I mean these these naming these variables, right? So now we are here. At this point we want to ask users if they want to which is the operation that they want to perform. This is what we want to ask them. So we can write exit. Oh, we did not do this could cost us. All right, damn it. Printf, let the users know that they have to do something. Select an operation. That's harsh. Is that which one of these operations do you want to perform? All right, this sounds fair enough. It's not that harsh. By the way, let's declare a variable. So let's say let's give some space. Int cell is supposed to get this input. We use scanf, of course. We use scanf, guys. We use scanfs. Scanf is used to sort of take input in C language if you don't know. And it's 1, 2, 3, or 4, right? It doesn't really matter. Let's do cell. So we are done. We have taken the input. And now we write the switch statement. Switch, and then it's gonna be cell, right? It's gonna be cell. This is what they have selected, right? In this case, if user has input, damn, is this how things are gonna be? I all right. If computer thinks that this is the, or if code blocks thinks this is the best way to indent stuff, I'm not going to complain about it. So case 1, what is it? Enqueue operation, and then there is break statement to end this. Case 2 is dequeue. So it's dequeue and break. Alright, we are here at the case 3. Case 3. What is case 3? Enqueue, dequeue, and then there is this peek operation that they can perform. Peeking and peeping are the same thing, guys. They might not be, but I think they are the same. Case 4 is break statement, or rather returns. Use return keyword to exit. Break this. Oh, do we need to though? Yeah, we need to. Now by default, what is it going to be? And now let them know invalid choice. Alright, so at this point they know that this is the error and that they need to continue. Then they have to write the program well. I write the good or nice operations. Now yes, no, the main one, right? Once you've done completing one of the cases, like let's say you choose enqueue, right? And at that point you want to dequeue, then Once you've done case 1 stuff, then the program will end normally. But at this point, if you want to continue, and if you continue, then you can do dequeue operations. So that's why I use this while loop. So as long as user wants this program to run, they will be able to. So that's why it is. Do you want to continue doing these operations? So if you enter 0, then it will end, and if you enter anything else, then it will not end. And at this point, do and what? Yes, no. Yeah, yes, no is declared after, or rather before, this whole do while statement. That's better way to do it. And it should give an error. I feel like I need to sleep. At this point, if user has uh, done all he or she can, then return 0. uh, that shows that the program was successful. Now we have to write these conditions, right? We have to write these conditions. We can write the condition so that they can keep in queuing as long as they want. But at this point, this is a simple program. So if you like, there's nothing that user need to think about this when it runs. You will be in here, you will be given options, you choose exit, the program will end right there. uh, you choose peek at the last data. If there is some data in there, then it will show the last data, and then if there is nothing in it, then it will print stack. Why do I keep saying damn, the last video was on stack, and that is a place from where I got the habit. By doing that video or recording that video, I got this habit of calling anything stack. So it will give the last data from the queue, and then dequeue or dequeue is an operation that you perform to sort of remove elements from the queue, right? And then in queue is supposed to put elements in there. So let's continue. Copy this one. We are going to write the code for in queuing elements. Later on we will improve this. This is not wrong, but in this case you'll be able to enter just one element or more than that. We can do it in the function too, right? Nah, but here it will be better because in function there are some codes that I don't want to get messy. It will be better if it's in here, the while loop, to continue doing this operation over and over again. Same thing for dequeue, but peak operation, there's only one element, which is the last element, and I mean the last element is only one, so you don't need to do peak operations over and over again. Why would you, in a proper sense, try to look at the same operation, do the same operation, and look at the same element? Oops. Why would you do that over and over again? Now, case 4. Case 4 is statement. Anyways, we copied that, right? Let's go ahead and paste it here. Now, this is the one that we want to perform. Alright, so let's do this. We are not taking anything now. Newly created model. Typecast. It's not node. Last time in the stack operation I did this error. It's not node, it's queue. It's queue. And then the asterisk sign, malloc function or malloc function, right? And after that there is the size of function. Struct. Oh damn it! Why do I've written so many programs in linked list in recent days. This is almost like a habit. Letting user know that they need to enter data. Actually taking the data as input. You can use this arrow operator to sort of access certain amount of certain location of the memory. What field? Data field. Node of next. I say it new node of next, but it's basically the next field of newly created node. Just get used to it, you guys. Now new node of next, null. There's nothing in there. If operation, checking if there is something in the list. If there's nothing in the list, then head is equal to new node. Now here we know at this point there is something in the list. We are not using head to traverse, right? We are not using head to traverse, but we can use tail here. It's better because every time a new element is added, it is the last element. So at this point head should be equal to tail. We don't want to use a temporary variable temp to traverse. We can just use tail to keep adding new elements. So when the first node is created, it will have null in its next field, and now the second data is created, right? The condition head is equal to null is false for the first time when the second data is added, right? At that point head has something in it, so if statement is false, we get to the else part, and in else part the tail is equal to the head. So that means we are saying that the first element's next field next field should contain the address of the second node that was added to the queue. So at this point, let's say head is pointing here to this first node, tail is pointing to this node, new node is pointing to the to this first node, and this is the condition when the first node was added. And after that, this when the second node was added to the queue, then this thing right here, this was empty, there was nothing in it. And when this node was created, new node, then its base address 900 was stored in here, right? And that is the code that I wrote right now. This line of code, right? This particular line of code was for that purpose. And now that something a reference has been added, a reference to the newly created node has been added, we should shift the tail pointer to the newly created node, because now we want to add another last element. Like every element that is added is the last element, right? So even the first element is the last element too at certain point. The second element, so the first element will be first element and the second element will be last element when two elements are there in the queue. So that's what I'm trying to say. So every time we need to update tail so that we can get to a point. So this is basically what we are going to do here. Keep adding these elements over and over again. And also, uh, what should we do here? Is there something special we should do to, I mean, we don't want to write an overflow condition. We want to allow users to add as many data as possible. So I guess this is fine. This is okay, right? This really is okay. Now let's do the dequeue operation, or write the code for dequeue operation. Now we already have, let's say what did I say about adding? We add from the beginnings, from the end. So there is nothing in the list here. There's nothing in the list here. Okay. And when the second node was created, its address was stored in the first node so that we can access it. So we are adding from the end. We are adding from the end. When there is new data will be added, then this null will contain the base address of that data, or that field, the whole field, the data plus next field. The base address will be stored in this node. So we are in queuing from the end. Now we want to dequeue from the beginning, right? So we already know that head is containing the base address of this one, so we can free head by creating a new variable. So let's say struct not node boys, it's gonna be queue. It's gonna be queue. I won't do the same mistake over and over again. So it's temp. Now let's say temp. Should we set it to head? No need to. Temp is equal to head. No need to do it in the same line. It's good even this way. Now the temp is pointing to head. We can move head around. Head is equal to head of next. Now I will explain this. What we did was we created another pointer variable which was pointing to the base address 100. Okay, so now we have two pointers here. One is temporary variable temp, another is head pointer, which is containing the base address of this one from the beginning. So these two are pointing over here. Now what we did is head is equal to head of next. So this is head, and what is head of next? Head of next is 900, and when we do head is equal to head of next, this 900 is assigned to head, and that means the base address of this node is assigned to head. So head is shifted here. Now head is pointing to the second node, and only temp is pointing to the first node. And in order to free this space, in order to delete this element, we can use the operation named free, the function named free. So let's do free temp. Now what happened is this data was deleted, and and the head was shifted to here. Now that temp is going to be deleted. And why is it going to be deleted? It is going to be deleted because temp is not in the main method. It's a function that we created. So in once that function is executed, the temporary variable will be destroyed basically. So this was the code to free the memory, or so to say dequeue. Now that dequeue is done, dequeue has happened folks. So at that point we want to do the peak operation. Tail is containing the base address of the last node, right? I told you guys, tail, listen, you know that this tail is containing the base address of this node. We want to access this data and we want to look at it. That is the peak operation, right? So what we do is like just print something, and that is the like uh, the data in the last node is 112 should be printed. That's what we want. Peak operation is for stacks, but we can use it in Q2. So tail is already, if head is not equal to null, because if there is nothing in there, if head is not equal to null, printf printf the data in the last node of the queue is percentage %d, and we are accessing the data part or data field of the last node using this tail. Let's get back here, write this thing, what should I call it, else part. If head is null, if head is null actually, if head is null, alright, what I would want to do is copy this, paste it here, right, take this, in this place we want to do this, because this will display only when head is empty. In that case only DQ operation will be performed. And why so? You can ask, and that's a fair question. Why so? Why would it happen? I should give you guys an explanation. If let's say there is nothing in head, right? There is null in head, then at that point we all know that there is no first node created, and when no first node was created, that means at that point there was nothing in the node, right? There was nothing, literally nothing in the node, and there was no first node in the first place, so DQ function will not work, and that means in that condition it will print queue is empty, and it's good. That's how it should be. Now very important function, display function, how it will work, let's see. We use temp, again temp is being used by us to traverse through the list here. Now at this point let's do while loop. Since last node is containing null in it, we keep doing this. When temp is not equal to null, by the way this will happen only not if head is not equal to null. Only in that case this should execute. Alright, what do we want here? While temp is not equal to null, printf percentage d slash n uh, temp of data, right? We are accessing the data. Temp is equal to temp of next. We are giving it the base address of the next node, so it can help. It can be used to traverse through the list. All right. At this point, we use the else condition. If there is nothing in the list, then we can print queue is empty. Slash n slash. Alright, so at this point we have done this, and this should be able. This should help us print things the way we want. Every time display function is called, temp is set to head, so there is no problem of temp not being head in the beginning. And if head has nothing in it, then this should execute. And if temp is not equal to null, then it should keep printing. And in the end, the temp will be equal to null, because temp of next of the last element, last node is containing null. So eventually temp will be set to null, and since temp is equal to null at some point, then this loop will break down. So that's how it's going to work. Now peaking, right? Now let's not do the display function here. Now at this point we can do it. Printf a after dequeuing de dequeuing or rather this is before, right? Before dequeuing, alright, at this point we want to call the display function. Display is the function that we want to call. Damn. Alright, so display function we want to call. Let's print it here. Sorry about that. Let's just copy this. At this point we have already displayed the data. Control plus C. Now that we have freed the memory from here, now we want to display what happened after dequeuing. So this is it. Now let's copy this one and do it here. Before enqueuing, there's a spelling mistake, who cares? Copy this, control plus B. After enqueuing, we call this function. At this point let's just try to do this. Let's check no errors, so pretty good. At this point we have done a great job. And now this is the program that we have written. First, which one of these operations do you want to perform? So what do we want to perform? Let's do peak operation, and it says queue is empty. Very good, very good. So it worked very well so far. Do you want to continue doing these operations? Yes, I do. All right, it gives me option over and over again, and that is very good. Now 2 is dq from the queue. All right, the queue is empty before queuing. Before dequeuing, queue is empty, queue is empty, and after dequeuing, queue is empty. There is some error, you guys. That's why it's doing it two times. There is something that I did which was stupid of me. I will have to see this. Do you want to continue? Yeah, I do. Let's do it one more times, you guys. Let's check this DQ operation. Yeah, there is definitely something in there that is error. So by running this program, we can see exit function will work perfectly well. I can bet anything on it. So let's do this exit function first. And yeah, it works pretty good. So at this point we saw took a look at these things. Let's see what's the error before dequeuing. It displays some stuff. So there is an error in the display function. Is that it? Else, and why does it do it? Why does it do two times? Look at it. Oh, look at this one. It happens two times because of this. There is one here. Eventually queue will be empty. In the beginning, since we have not added anything, this is the error it will give. And since we are not using the peak operation, let's not do this else part. Or let's remove this else part. Then things should be better. Yeah, we should remove this one. Perfect, perfect, perfect. Let's go. F2 to see. Yeah, pretty good. Now let's run this and let's do 2. Yeah, this is good. This is good. Queue is empty. After dequeuing, queue is empty. There's nothing in there. Dequeuing didn't even happen. So yeah, perhaps this is well arguable because there was no dequeuing, right? So we will have to think about how to write this logic so that things work perfectly. But this is I just did this to make sure that there's nothing error type happening in queue operation. Yeah, I want to continue doing operations. For that was one for that. Now, uh, which operation do you want to do? It's in queue. Before in queuing, queue is empty. Let's add 100 to it. After in queuing 100, do you want to continue doing this operation? Yes. Which one do you want to do in queue? What do you want to enter? Before in queuing, there is some data in there. Uh, there's some data in there, 100. Let's add 500 to the queue. Let's say where does it add? All right, so you can see that it is in queue. Now let's continue doing these operations. Let's in queue. And what do we want to in queue at this point? Let's add 99 in there. All right, 99 is added. Now let's continue doing these operations. Which one do you want to do? So in queue is the operation that I want to do one more time. Let's do uh, 200, right? Now at this point, yes, I do want to continue doing these operations. Which one do you want to do? 3. Third operation, we want to do peak. Now we want to see 200 over there. We want to see 200. The data in the last node of the queue is 200. Perfect, perfect, absolutely perfect. This is gorgeous. This is working very well. Now do you want to continue doing these operations? I should probably give some space in there. Look at this. This is so awkward. I mean, it's it's so like close to each other that it's not very clear. So I think I would need to do that later on. I'll do it. Right now the video is already like an hour long, so I'm not really going to drag it even longer. Do you want to continue doing these operations? Yes, I do want to. I haven't even checked the DQ operation yet. So we want to remove 100. The element at the top of the queue should be removed because the elements are being enqueued from the last, but they should be dequeued from the top. The first element that was in the queue, that came in the queue, that was entered in the queue, was 100, and the first element that should get out of the queue, that should be removed of the queue, is 100, because this is first in first out. So let's do this which operation do you want to perform? 2. I want to dequeue, and before dequeuing it's 100, 500, 99, 200. After dequeuing, head is set to 500, and then there is 99 and 200. So first in first out, the first data was removed from the list. Now do you want to continue doing these operations? Yes, I do want to. Which one do you want to do? 2. I want to do dequeue operation, and only 99 and 200 is left. Let's do one more time. DQ. Oh, sorry about that. Invalid choice. Yes. Uh, which, yeah, that just shows you that there is the case for it. When you have written wrong, when you have chosen wrong option, then there is this invalid choice option. So perfect, that is the default choice. So it's better that we tested it, right? So one of these operations, do you I want to DQ. Yeah, so in before dequeuing there was like this 99 and 200, and after dequeuing only 200 is left. So in the beginning we added 100, 500, 99 and 200, and then we kept removing, and the element from the top of the stack keeps getting deleted, and in the end there is only 200 left, which was added last. So it's also last in last out. The element that was, and that was like inputted, or not inputted, or rather written, right, or saved, or whatever you want to call it, put in the queue in the last, was go or is going to be removed last. So let's do 2. And before dequeuing there is 200 in there, and after dequeuing this queue is empty, nothing is there. So do you want to continue doing these operations? Yes. Which operation do you want to perform? Exit operation. You guys can see that it is working perfectly. Listen, what I can do is that at a certain point when we are in queuing, we can continue in queuing as long as user wants. So we can write a condition here, a while loop that will run as long as user wants to in queue. So at the same time we can keep adding 100 or 200, or as many as the elements that can be added. So the condition of overflow is reached. We can keep adding till then. So that will depend upon users. If they want to break the loop, then they can do it. So we can write the code for that too, but at this point that seems pretty unnecessary, or not unnecessary. Let's say you want to upgrade this program, then you would want to do that, huh? So what should I do? The video is already 1 hour long, or even longer. Should I do it? Should I do it? Should I do it? Nah, let's leave it. We have already done it, and it's working perfectly. At this point the video is gone way too long. I will upload another video on it, show you guys the code. um, for now this worked very well. This worked really well. This is beyond what I expected. I thought there would be some errors, but I had already uh, written these things. I had already everything planned. Let me tell you guys this: I have not written the code down on my copy, and I'm just texting. As you guys could see, I was naturally doing everything, uh, and there were some errors, and I fixed them too. uh, and I learned a lot when I wrote this program, this linked list implementation of stacks, and I learned a lot from that. and because of that I was able to write this program very easily, the queue operation. So I'm really happy about it, and I'm happy that this video turned out good. I hope you guys enjoy it. Thanks a lot. Now let's end this video.